Welcome to Intelligent Systems, an introduction to artificial intelligence. In this video, we will look into entity recognition with hidden Markov models. In the previous lecture, we learned how to use string algorithms to identify entities in text, and this could not handle ambiguity. And we'll now introduce a very simple mechanism that can use context of an entity and decode this, and the technique is called hidden Markov models. So take as an example the city Denver and the name Denver, as in John Denver, country roads take me home, for example. So when we have a sentence like Oscar went to Denver, did he go to the city or did he see somebody called Denver? So we want to resolve this ambiguity by taking the context of the entity into account. And one technique how to do that is called hidden Markov models, because it infers from a sequence of observations like Oscar went to Denver, a sequence of states like the first item is a person, then something else, and the last entity is a location. And the idea of these hidden Markov models are that we have emission probabilities. So in a given state, there are certain probabilities of emitting observations. So for example, in the state person, there's a certain probability that the observation Oscar will be emitted. But there might be also other names like Peter, Mary, Jane, and so on. Or the state other emits went. And then we have transition probabilities, and those are probabilities of how we change from one state to another. So how likely is it, for example, that the state person is succeeded directly by a state location? And this is how hidden Markov models can be formalized. So we have here a quadruple, and let's go one by one through what these different items mean. We have a set of states, like for example, person, location, start state, end state, other. We have an alphabet, so those are the observations we can make, like Denver, Colorado, Paris, John, and so on. And then we have state transition probabilities. So how likely is it that we go from the start state into location, or from location we remain in location, or from location we go to state other? And emission probabilities. So for example, in state location, we emit Denver or Colorado or Paris. And we have initial state probabilities, so we must have a beginning. How likely is it that we start our sequence in the state person or in the start state? And these A, B, and pi are probabilities because the sum over all states in I is 1. And the sum over all possibilities of transitions from I to J must be 1. And the probability of all emissions in all states must also amount to 1. Now let's look into this more concretely with an example. So we have here the start symbol $, and the end symbol euro, and John Denver will be playing in Denver. And we have another sentence. Denver is a city in Colorado. John and Paris went to Washington. The Oscar goes to Denzel, Washington. Oscar lives in Washington. And you see all of this ambiguity. Oscar here is a prize, here it is a person. Paris is over here, not a city, but it's rather a person. Washington is not a name, but it's rather a location, right? So we have plenty of examples here where sometimes a word is a location, sometimes it's something else, and sometimes it's a person. This is our training data. So important, hidden Markov models are a supervised technique. That means we need training data. And that means somebody sat down and labeled these sentences and gave us a sequence of states that is correct, which is here, for example, start, person, other, location, end. or here start, location, 4 times other, location, end. We do have something known, and that is that we begin our sequence of states in the start state. So the start state has probability of 1. And now the big question is, what are the probabilities of all of the other states? So we begin in the start state, but how likely is it that we move from the start state to person, or from start to location, or from start to other? And this we can infer. This is our training data, and so we can see we went to person 1, 2, 3 times, and to location once, and to other also once. So 3/5 is this probability, 1/5 is state to location, 1/5 is start to other. And this we can continue and do for all of the other probabilities that are needed in this transition system as well. So for example, person to person, 1 occurrence, here it's person to other, person to other, person to person twice, and person to other. We have also here person to end. Yeah, and so overall we have 7 transitions from person, and twice we stay in person if we have been to person before. So that means this arrow over here has a probability of 2 divided by 7. We didn't see a single time that we moved directly from person to location, so that probability is 4. And from person to other was very likely. That happened 4 out of 7 times, and once we made it to the end state, that was 1 out of 7 times. And this goes on. So here for location to end, and you see location to end happens quite frequently. So after seeing a location 4 out of 5 times, we go into the end state. And to complete the picture, here are the numbers for other. Other was very, very frequent. Overall, we had 17 transitions starting with the other state, and the most likely was that we remained in the other state with 11 out of 17. Location came after other 4 out of 17 times, and person only 2 out of 17 times. So how can we estimate the emission probability? So we want to know how likely it is that we see a certain observation in a given state. And for that we can have the associations given over here. We see, for example, that in person, once we had John, once we had Denver, once we had John over here, so that means it's the second time already. And that means for the state P, we have John 2 out of 7 times. Denver, we had 1 out of 7 times. Denzel, 1 out of 7 times. Paris, 1 out of 7 times, and so on and so on. The start symbol had a probability of 1. We had 5 occurrences of the start symbol, $, and it was always in the state S. And the same for the end symbol. Now, the question is, what is the probability of an observation sequence O and a state sequence S? So what is the likelihood that the state sequence S is producing the observations O? So basically, P of S and O is equal to the probability of being in state S times the probability of making the observations O, given that we're in the states S. And that amounts, and we can unravel it, if we assume independence, to the probability of being in state S0 times the probability of seeing observation O0 and state O0 times, and then we simply multiply all of this up step by step. The product of t for time from observation 1 to the last observation, length of the sequence of observations O, and we multiply the probability that we were in state ST minus 1, and we're now in state ST, and in state ST we made the observation OT. So let's apply this formula and see how likely it is that the state sequence start, other, person, end generates the observation start symbol, Oscar went to Denver, end symbol. So we want to calculate P S, O, and we're using this formula over here. So let's do this now one by one. So we're starting in t equals 0, and that means we're making the observation of the start symbol. And and we have an initial likelihood of being in the start state of 1 and making the observation of the start symbol in the start state is also 1, so that means that likelihood is 1. Now we're going to the first real observation that we're making, and that's the word Oscar. Now, we want to know what is the likelihood of going from start state to other. So that is from here S to other, that's 1/5. And in the other state, we're making the observation Oscar, that's 1/17. So that means we multiply the one we had already times 1/5 times 1/17. And we're now with the next word, and time has moved forward by 1, we're at went. And that means we have gone from other to other, and in other we observed went. From other to other has a likelihood of 11/17, and observing in the state other went has a likelihood of 1/17. So we multiply these two values over here and expand our overall likelihood by this term. So something similar happens for Denver. Now we're going from other to P. So other to person is, I think, 4/5. That's this arc over here. And in person to observe Denver has a probability of 1/7. So 2/17. Yeah, that was the likelihood over here, times 1/7. That was the likelihood over there. And then finally, we want to know what is the likelihood of going from person to end and seeing the end symbol in the final state. And from person to end has a probability of 1/7, and observing end symbol in the end state is 1. So 1/7 times 1, and then we can calculate this, and we get 8.18 times 10 to the power of -8. So that is the likelihood of this state producing that sequence. But obviously that is not very good, right? We just have a number here, but if you would have asked us, Oscar went to Denver, then you would probably have said, well, Oscar is clearly a name, went and to are other, and Denver, yeah, could be a city, but could also be a name, and then you would just pick one of the two. But that sequence here, you would definitely intuitively consider as unlikely. So how can we determine that? Well, obviously, we can write down all of the possibilities of sequences that could have produced our sentence, Oscar went to Denver. And for one, we have calculated already the likelihood. And one of you maybe have said, okay, person, other person is the thing. Somebody else would have said person, other location is the thing. We just need to calculate all of these probabilities. And then, of course, also those probabilities that are even more unlikely, like other location. Now, the big problem with this is that we have, again, as we have seen many times in this course, a state explosion that is problematic in practice, because the moment we have even modest-sized examples, we cannot really handle this state explosion. So if we assume that the sequences have length n, and we have an amount of s states, then basically s to the power of n is what we're dealing with. And even for our trivial example of n equals 6, and there just being 5 states, it means there are 15,000 possibilities that we have to consider. Yeah, so even for this trivial example, this is already quite a staggering calculation. And of course, we know right away that there are parts in this calculation that make no sense at all, because we know that the start state must be in the beginning. It makes no sense at all to have the start state in the middle and the end state at the beginning. So that can be excluded right away. We know this S comes first, E comes last. And over this, of course, there might be a dispute. So how can we maximize the state sequence to get the highest likelihood PSO? And for that, there is an algorithm called the Viterbi algorithm that is very old. It comes from the late 60s. And that uses dynamic programming in order to calculate this likelihood. So the key insight is really just that we formulate these probabilities as a recursive formula, and the recursion we handle by storing intermediate results in a matrix. So let's see what the recursion is looking like. So we have a base case which considers the probability of emitting the start symbol. So this will be very, very simple, because only in the start state we're emitting the start symbol, and any others we don't, and that means they're all zero. And then we have kind of the true workhorse, that's the recursion. So the probability of a state, and now really comes the important bit to which you have to pay attention, is the highest probability after making our previous observation. So we've moved one time step forward, and times the probability of making the transition from the state that gave us this high probability in the previous observation. So how likely is it to make the transition to the current state? And then we have to multiply this by the probability to see the observation we're seeing in the current state. So those three terms get multiplied, and we maximize over those two. Yeah, because both of them refer to the state in the previous observation, and this considers only the current observation, so we don't need to maximize over that. Now let's turn this intuitive description of the formula into notation, and we use an uppercase pi for the initial state probabilities, A for the transition probabilities, B for the emission probabilities, and the indices J and R, they range over states, and index I ranges over observations. And that's what we get. So what we want to compute overall is f of ji, where I is an index for an observation. So ultimately, we want to have that probability for the last observation in our sequence. And j is the index of a state, or is a state. So let's consider the base case. Fj0 is equal to the initial state probability of that state j times the probability of emitting in state j the first observation. Yeah, and the first observation is always the start symbol. So this 0 means here start symbol. So how likely is it that in j we observe the start symbol, and that likelihood is 1 for the start state, and for all others it's 0. And we have only one start state, so that would have the initial probability of 1, and all the others would have 0. So that is a fairly trivial and easy to compute case. But now comes the recursion. Now let's turn that into formulae, and what we have is fji is equal to the maximum over states r, and we have in the previous observation I minus 1 gotten the probability for state r, and we multiply this by the transition probability of going from r to j, and the transition probability is indicated by a. Over this we maximize, and then we multiply this whole optimized transition by the likelihood of being in state j and seeing observation I. Yeah, so even if this may be very likely, if it's not likely to make observation I in the state j, this will be, let's say, in the worst case, 0. And even if the likelihood of seeing I and j would be very high, if the likelihood of getting there is low, then the whole thing is also low. Yeah? And so once again here, the highest probability after previous observation, so this was basically the best we got from the previous observation, times making the transition to the current state, times to seeing our observation in the current state. So this recursive formula f can be computed with dynamic programming, and that's the essence of the Viterbi algorithm, because we've seen previously the state explosion, and that means that essentially computing these probabilities is impossible. But with dynamic programming, it becomes tractable because we store intermediate results, and ultimately we can reduce the size of the problem to a complexity of number of states times number of observations. So we're using dynamic programming, storing intermediate results to compute f efficiently, and a matrix has signs number of states times number of observations. And an important thing is also natural language processing. S and O are typically not very large. You know, how long is the longest sentence you can imagine? There's, of course, in literature you can find funny examples of whole books that run pages and pages and pages in its one sentence. But typically a sentence is quite short, 10 words, 20 words, 50 words will be already a very long sentence. And how many different states do we have? Maybe it's a handful different states. So that means those two numbers are very low, and that makes this algorithm quite attractive. So let's do this now in practice for our concrete example of Oscar went to Denver. So here's our matrix, and important here on the x-axis we got the observations. So from 0 to 5, we have 4 different words, and then the last observation is the end state, is the end symbol, the first observation is the start symbol. And we have 5 different states, PLO, proper ones, person, location, other, but also the start state and the end state. We initialize over here with this formula, and only in the start state, making the observation of the start symbol, we get for this formula 1. Both terms are 1, so it's 1 times 1. And for the other cases, it's 0 times 0. Yeah, so that is the base case. And then all of this is computed from this formula over here. And we proceed by going from 0 to 1, from 1 to 2, 2 to 3, and so on, in the observations. That means we're starting here, and it doesn't really matter in which order we're picking here the states. So that means I has incremented from 0 to 1, and we're now considering this case here where I is greater 0. So I is equal 1, and we're calculating all fj1. And they amount to the maximum R for fr0, so we're pointing back here, and we're considering all of these R. So R is basically successively taking S, P, L, O, E as value. We multiply by the transition to one of these states and multiply that with the emission probability. So essentially, we have to do in this step here, to fill in this, we have to consider all against all previous ones. So that means here, for example, the maximum is obviously coming from the start state, and turns out that person was the most likely. And after calculating all of these probabilities, 8.5 times 10 to the power of minus 2 was the best probability we could achieve. 3 times 0, and this time here is not as good. And in this manner, we iterate through this matrix, and we get the assignment SPOOLE as the most likelihood, as the most probable one. So that means for the data, just the handful of examples we had, the most likely explanation of the observation Oscar went to Denver is that Oscar is a person when two are other, and Denver is actually a location and not a person. Now, an important question is, does choosing the maximal value here, the maximal state R, always lead us to the optimal path? And this can be easily proven by assuming that it's not the case. So let's say that that actually the path that we took by picking the maximum was not the optimal path. So besides the one that we calculated with our formula, which is depicted in red, there's actually an optimal path depicted here in green. Now, at some point, the optimal path and the path we calculated, they must have deviated if the path we calculated is not the optimal one. So there must be this cell over here where the two paths deviate from each other. So that means we have one part that might be empty here, but it might also go very, very long way where both paths agreed. But then at some point, as we're moving from right back to left, there was a first disagreement between the optimal path and the one that we calculated. Now, if that were the case, then what must have happened is that we got here together with both paths in state J. And since we're coming from two different states, we were here in our red path at, let's say, H. So basically this here would be H. So FHI minus 1 times transition probability from H to J, because we're maximizing, and that's why we have picked the red one. So because we took the maximum, this is higher than coming from G to the cell J. Yeah? So coming from G, so this is called G here, and that was the optimal path that came from G. Yeah, and the reason it came from G is that it had f of Gi minus 1, so that's the value over here, times the transition probability of going from G to J. But because of our maximum calculation, we know that this term is higher than that term. So that is just known. Now, let's consider the total probability. The probability of seeing observation O with state sequence S, and green again optimal, and on the other hand, our supposedly non-optimal red one over here, they're equal to this probability and this probability times the rest probability for this part. PR is this over here. Yeah? So this is a true equal symbol here. So those are the same. Now, since the remaining probability, this part here, was in common to both of them, we have a contradiction. Yeah? On the one hand, we know that through the maximum calculation, the red part is bigger than the green part. This is the exact formal definition of those overall probabilities. And from this and this, we can infer that POS prime is bigger than POS. And that is contradictory to our assumption that POS is the optimal path. So it's not the optimal path. So that's the proof that our algorithm has calculated the optimal explanation for the observations that we're making. So take-home message: hidden Markov models can infer from a sequence of observations a sequence of states. The Viterbi algorithm computes the optimal sequence of states for a given sequence of observations, and it uses dynamic programming and stores the intermediate results in a matrix. And a matrix has dimensions of number of states times number of observations.